I am here at Universal Radio in Columbus, Ohio. I really appreciate the opportunity to be here, and I thank you for switching over to the second video discussing the physics, the science, and technology of this antenna. I will be discussing the science and technology historically of other patented inventions that I have derived to give a fuller understanding of those phenomenal antennas, as well as this particular COMPACtenna design, which meets the applications where one must have a very reduced size antenna, yet they just cannot tolerate the generally otherwise poor performance one gets with standard antenna technology in a reduced size. I'm going to talk about reliable range. Now you may say, well, there's range. Is there a difference between range and reliable range? The answer is yes, and that's very key. When we talk about range in the line of sight environment, what are we talking about? What's important? Well, let's look at an example. Let's say that we're going from the top of one mountain to the top of another mountain, and we have the communication. We are essentially line of sight. Sure, there is atmosphere in between, and the atmosphere does cause disturbances in the electromagnetic wave. But discounting that for the moment, and of course it depends on frequency and distances and all of these kind of things and the actual atmospheric conditions, but discounting that for a moment, gain is everything. So for example, if you want to have the same communication level and you want to get to the next mountaintop, you need to increase the gain of the antenna. But the point is that on Earth here, when we're communicating, we are 99% of the time non-line of sight. We're non-line of sight. We have all kinds of obstructions. We have natural obstructions, such as hills, down in valleys, trees. We have man-made obstructions. We may be in the center of a city with buildings all around. This is a very non-line of sight environment. So what we wind up having is what we call flutter or picket fencing in the analog communication. This problem is even worse in digital communication, where we can get packet errors, and we then wind up having retries. We have slowdown in the overall throughput, even drop in the connectivity. So it's both an analog and a digital communication problem. The goal that I had was to improve that. So in order to improve something, we need to understand first what is the cause of the problem. Once we establish the cause of the problem, then we need to try to fix it. All right? So just before I get into that, let me make a commentary about the reliable range. Reliable range can be predicted based on propagation analysis programs, which many of us are familiar with, where with the software, we plug in the gains of the antennas, the amount of power transmitted, the losses of the coax, the distances, the loss based on the distance, even terrain factors can be plugged into more sophisticated software programs. We see it in the real world environment, and the better the program, the better it mimics what occurs as we do the site surveys. So what we see as an example, very roughly, if we're looking at the top and we have a tower and we have an antenna, and then we have the terrain around it, we see that we don't get a range of communication that's a perfect circle. Not at all. We don't see that at all. Instead, we see such things as this kind of a thing. And in fact, at times, we'll even see holes in that communication. And arbitrarily, we can use the 95% reliable range. 95% reliable range, which means that 95% of the time when we talk and we listen, we have good communication, 5% we don't. It's arbitrarily 95%, but we'll go with that. So what happens is when we get past that point, then we have too much fluttering, we have too much picket fencing, we have too much in the way of dropouts and loss of connectivity. It's not reliable. This is really important for government, municipal, state, federal, military communications, high-profile commercial communications, but it's important to us hams as well. It's important because as we're traveling along and we're dealing with the traffic and the conditions, it can be very frustrating and it can even be dangerous in trying to have the communication that we can't have because of the lack of the reliability. So the goal is to try to take these areas where there are dropouts, and these occur, for example, when you're down in a valley, down by the riverbed, for example. It occurs when you have buildings around that are blocking the communication. What we want to do is try to extend that reliable range and get rid of the dropouts as much as we possibly can. How are we going to do that? To do that, we need to take a look at what is actually happening. Let's look at it from this perspective. Now, when we look at the amount of signal that we're getting, or signal to noise ratio, or RSSI, we can essentially create a graph. There's a certain minimum signal necessary to maintain the connectivity. This may be at different levels depending on the communication we're having. Typically, the higher the frequency, typically the more digital the communication, the higher the dBm rating necessary to maintain that connectivity, especially with greater throughput. So this can be a variety of different numbers, but say, for example, in this case, it was a minus 95 dBm, 95 dB below milliwatt. Again, the greater the number, actually the lesser the signal because it's on the minus side. So what happens when we're communicating? Typically we have what's built in, and it's an arbitrary thing again, because of the standard technology, we build in what we call a 15 dB fade margin in order to create this reliability. Okay? So what it means essentially is that here we have minus 80 dBm. And again, these numbers can shift down, they can shift up, it depends on the type of communication. Because here's the thing, again, this is the minimum necessary, but this is pretty much your average, let's say, mean, median, whatever, average signal strength that we have. We have intermittent drops in that signal strength. As we're traveling along, or even staying in one place with the dynamic obstructed environment around us. What does that mean? Well, it's very simple. People moving around, vehicles moving around you, doors opening and closing. This applies to everything. This applies to outside communication, outside to inside, inside to inside. It applies to everything. We have a dynamic obstructed environment. So we have fluctuations in the signal, and the signal varies. Well, unfortunately, what happens at that line of 95% reliability, and also closer and further away, but say at that line, we have this was what I was focused on a couple of decades ago. We have intermittent millisecond or otherwise drops that are very substantial. That's what causes the fluttering. That's what causes the picket fencing. That's what causes the packet retries and the drop in throughput and the drop in connectivity. You see, it's significantly below that 15 dB fade margin. So I took a look at that and I said, well, in that case, how do we improve this? How do we extend that reliable range? Well, if we were, for example, to say, let's use a higher gain antenna. Well, one of the problems with higher gain antennas, vehicle, base station, otherwise, is that, of course, as we know, typically, it compresses the elevation coordinate pattern. Well, what does that mean? Well, if you have a quarter wave antenna, you may have a pattern such as this with the gain such as that. And if we go to a half wave or a 5/8 wave, we get somewhat more gain, but we get a compressed elevation coordinate pattern. So what happens is you're focusing the signal. And unfortunately, sometimes that gain actually works against us in the obstructed environment. If you're down in a valley, then this increased gain is just going to shoot into the hillside, as opposed to being able to reach above and diffract and refract and scatter and whatnot. So even so, let's say that we increase the gain and the gain was effective in its patterning. Say, all right, we go a few dB higher. There becomes our average signal. Maybe, actually not, but maybe. Well, all right, then we increase these by a few dB. You're still significantly below here. These drops are on the order of 20 to 30 dBm. 20 to 30 dBm. It's a logarithmic equation. So you drop 10 dB and you're at 1/10 the signal. You drop 20 dB, you're 1/10 squared 100, and 30 dB, 1/10 to the third power, which is 1/1000th the amount of signal. So you're really not doing a lot to this problem at all. And I noted that, experimenting with a number of different antennas. So the focus then becomes on not this really, but this, because if we were simply able to get these drops to even 1/10 the amount of our average signal, just 1/10, 10 dB down, we would be above that minimum level of connectivity. So now, even if we dropped the gain of the antenna, the peak gain, depending on the pattern of the antenna, well, then we would have more of this kind of a thing, and we would more consistently be above the minimum signal necessary to maintain connectivity. Now, this is a totally different way of looking at it, but that should work. That should take that 95% reliable range and bring it out further. Okay, let's go on that. That's the theory. That's the postulate. If this is true, then what we have to do is we have to figure out what is it that causes those drops that significantly. Well, one thing is hams we know is this. If we have a vertical antenna and we're communicating with a vertically polarized antenna, all is well. If we then turn that antenna sideways and we go to this, we lose what? Well, the textbooks will tell you 20 dB or more. It's actually 1 over infinity, but because there's actual physical structure to the antenna, etc., it isn't quite 1 over infinity. It's about 1/100th, 1/1000th, 20, 30 dB drop. So as the signal then in our real world environment where we can't see the tower, which is again 99% of the time, or vehicle to vehicle to handheld, whatever the case may be, if the problem is polarization changes, well then that could account for it. Well, do we see polarization changes? Of course we do. We know this in HF communication, that with skip, ionospheric refraction, we see polarization changes, and that's why oftentimes a vertically polarized quarter wave antenna will do quite well, even to a horizontally polarized other station, because there's flip-flop that's occurring all the time in the polarization. We also see polarization changes when we communicate to space, and we go through the ionosphere, etc. We see Faraday polarization shifting. So in the environment, we get reflections of the signal, we get refractions of the signal, we get diffraction. We all know about that, knife edge diffraction, Fresnel zone, and that kind of thing. We know about this. The theory is, okay, we have polarization changes that are occurring in this obstructed environment, particularly when we get into those difficult to communicate areas. So we would need to fix that. What else? And by the way, just as a little side note, You may think right away, circular polarization, both the X and the Y axis. Circular polarization developed about 50 or 60 years ago, was utilized originally so that we could double the amount of information that was being utilized on the same frequency. Some of it in the one polarization, circularly polarized, and the other at the right hand versus left hand kind of signal. As it turns out, of course, there is Faraday polarization shifting in the ionosphere, so there's more to it than just was originally thought. Eventually, in the Wi-Fi arena, people started experimenting with circularly polarized antennas, and they found, oh yes, much better in the line of sight, gets through the trees better, and that kind of thing. Okay, so that's a side note. This is actually easier for me to discuss than it was 20, 25 years ago, because it was such a paradigm shift that there were a few that embraced it tremendously, and others that just thought it was too out of the box. But so many things have occurred since then that it becomes easier to talk about, particularly in the electronic world, where we went from, for example, we had a Wi-Fi wireless router, in your home or your office, and it had a single, at the most 2.2 dBi rubber duck antenna on it. And then we saw longer antennas and longer replacement antennas. And then later, we started seeing two of those little rubber duck antennas on there. And we saw receive diversity, full transmit diversity, MIMO type N communication of one of the three various types. And of course, they advertise greater range, right? But they never talk about the gain of the antenna. Of course not, because it's not the gain of the antenna. It's the diversity that is causing the gain. Well, we're going to be talking about creating diversity in the antenna itself with a singular feed, which works in and of itself, but of course also works synergistically with the electronics that was developed while I was developing the antenna with a single feed. So anyway, sorry to jump off, but that's an important note. So might there be another problem? Indeed, there is another problem, and we've known about it forever. Uh, and what do we call it? We call it multipath. We call it multipath, and most of us know all about what multipath is. But to keep the video of the explanation as short as possible, we have a transmitter here and a receiver over here, and we have all kinds of obstructions in between. Oftentimes, the signal that we're utilizing is not the direct path signal whatsoever. It's actually reflected signal off of a building, say, for example. But guess what? There's another building over here and another path that occurs. So what happens is you have the sine wave coming along, and if you're in just the wrong spot, or the dynamic environment, at that moment you're at the wrong spot, what happens is the one wave is such as this and the other wave is such as that, and they cancel out, and that's multipath cancellation. We've never done anything about it because, again, the antennas were all built the same way. Shorter, longer, higher gain, tighter elevation coordinate pattern, whatever the case may be. So we know about this problem, multipath. And multipath can absolutely create 20, 30, even more dB drops in the signal. So we've got two problems here. We've got multipath and we've got polarization changes. We need to fix that. So now what I'm actually going to discuss is the basics of other designs in my history that are wonderful in significantly being able to improve this. MP antenna has this product. So how do we fix it? Well, the way to fix it is to develop a three-dimensional antenna. You're thinking three-dimensionally, you must construct three-dimensionally. So let's go first to the multipath problem. You look at the top of the vehicle roof. You could certainly put an antenna here and put an antenna here, but you also have to put an antenna here because you're going to have both problems left to right as well as front and back. We've all been there. We listen to a station. We enjoyed the program. We pull up to the stoplight. The signal goes away. Multipath problem. We take the foot off the brake. We creep forward a little bit, and there's the signal again. But you're going to have an array of antennas up here, and it's just It's just not, appropriate. So the bottom line is, I'm going to jump to this, that if we have the feed point of the antenna here, we're looking at the side, and we go with more than two elements, 3 different elements. Then, if one of the elements is in a null spot, we're talking about the electric field here. If the one element is in a null spot, the other antenna element is in a hot spot, both side to side and front to back. What about the polarization problem? If we have 2 elements and we connect them and they're exactly the same like this, we get a slant polarization here and a slant polarization here, and it summates to a vertical polarization. We haven't created any polarization diversity yet. If we do something different than circular polarization, and we make the one element a little shorter than the other element, the alternating sine wave comes up the coax, comes out to the tip of the antenna at the high voltage point. It's going to hit here first before it hits here. So at that particular moment, you're going to have a stronger field in the electric wave here on the slant than you are in this one. And you will wind up with slant polarization. Furthermore, by having 3 of them connected like this or more, as you turn it, you can see that similarly to circular polarization, where you have a quarter wave separation between the horizontal and the vertical element, and you have slant elements, you get a different slant polarization in time and space relative to each of the elements, and you create polarization diversity. So this is a way, that's a very simple explanation to the polarization and the spatial diversity that you get. The power is in the diversity, it is not in the gain. Now that said, slant elements couple very well with ground planes to increase gain and effective patterning. But, all right, keeping it short, that was the theory, and it worked. All right, so that's great, and that's out there. What about, though, for the applications for the people that just have to have a smaller antenna, even smaller than that? But they don't want the poor performance, like with a handheld, you go with a standard antenna, you go down to a stubby duck, and yeah, it's convenient, but the performance is poor. Vehicle antennas, you go from standard antennas down to patch antennas, disc antennas, loaded quarter waves. We all know what the performance is. Sure, it's aesthetic and great in terms of low line obstructions, but the performance is poor. So how are we going to do this? We got a COMPACtenna, which means that we're not going to have much in the way of the spatial diversity, the 3-dimensional characteristics. It's inherent in the name, in the nomenclature. We certainly don't have vertical diversity anymore. We don't have much in the way of horizontal spatial diversity, a little bit, but not much. It's one thing to develop it, and that's wonderful, being smaller and being multi-banded. That's a feat. The other antennas we see out there, they can be quite expensive. They may be short. Again, not great in performance, and aren't multi-band. And in the band that they cover, they don't cover many frequencies. But this does. Again, I alluded to it before. There's a lot going on in there, both directly and indirectly connected. A lot of electric and magnetic field coupling. So how are we going to do it? Yeah, the answer is the magnetic field. Oh boy, what do you mean magnetic field? Well, first of all, electromagnetism, radio frequency. When we generate power and we generate radio waves, half of the energy is in the electric field. Half of the energy is in the magnetic field. If we're not utilizing it, we're wasting it. That is the answer. But wait a minute, that's out of the box because, well, certainly we have small electric or magnetic loop antennas for receive, we know they're not very efficient. They only work in the near field, right? Right? Near or near to midfield, you know, calculated by 2d squared, the distance between divided by the wavelength and whatnot. How are we going to do this? Well, the answer is we have to effectively utilize the magnetic field. The mind block on this is that the electric field decreases by the square of the inverse of the radius away from the exciter, the antenna itself, as we go away from it. And of course it does, because radio waves don't just go like this, they go like this and they go like this, right, in the electric field. So it's like a sheet of paper coming at you. The x times the y, or the x times r times the r, it's like a plane that goes away. But the magnetic field is the cube of the inverse of the radius. So it decreases more rapidly. And if we go back to that whole discussion about this, and if we find that if we can we could utilize the magnetic field effectively, and even if we only increase the significant dropouts by a certain number of dBs, even though it's less than we'd be able to do with the electric field, then theoretically it would be possible to do this kind of a thing. Well, that's what it is. That's what it's all about. It's utilizing the magnetic field effectively. Think Tesla on steroids. That's what's going on in there. By effectively utilizing the magnetic field, theoretically, we would also be able to increase the reliable range to the point that now you not only have a compact antenna that works decently, it actually works better in the real world we live in, obstructed environment, than even full-size antennas. And for those needs where you just absolutely have to have a compact antenna, you now have a solution where before you didn't have one. I thank you for listening. I think I'll stop there, but always free to come and speak in greater detail. I thank Universal Radio again, Fred Osterman and his team. It's been a delight coming down to Columbus, Ohio.